Good morning. My name is T. Simbil Ganesh. I am assistant professor in the Department of Physics. Now I am going to teach about the semiconductor physics. Let's uh, find out what are the topics to be deal now. First, I want to see about the introduction about the semiconductor physics, types of semiconductors, and the intrinsic semiconductors, energy band diagram, direct and indirect band semiconductors, carrier generation, in intrinsic semiconductors, extrinsic semiconductors, carrier concentration in N-type and P-type semiconductors, Hall effect theory, both N-type and P-type, and its experiment, and also the applications of the Hall effect. Now, the introduction about the semiconductors. Semiconductors are nothing but the materials whose electronic properties are intermediate between those of the metals and the insulators, that is, the conductors and insulators. Once again, I have to repeat that semiconductors are the materials whose electronic properties are intermediate between those of metals and insulators. They have the conductivity in the range of 10 to the power of minus 4 to 10 to the power of plus 4 ohm per meter. The conductivity is very effective. That is in the range between the that is metals, that is conductors and the insulators. The interesting phenomenon about the semiconductor is that they are bipolar. Bipolar means two, and the current is transported by two charge carriers of opposite signs, that is plus and minus, negative and that is positive, that is electrons and holes. These intermediate properties are different, determined by the own crystal structure bonding characteristics. Let us now deal about the more points about the semiconductors. Silicons and germanium are the most best example for the semiconductors, as we have well known that because the silicon have and the germanium also have the four valence electrons which are distributed among the outermost s and p orbitals. That is, valence electron means the outermost orbitals having four electrons in the outermost orbit. That the number of electrons deciding the valence electrons. These outermost s and p orbitals of semiconductors involves in the sp3 hybridization. These sp3 orbitals form four covalent bonds of equal angular separation, leading to a tetrahedral arrangement of atoms in space. Results the tetrahedron shape, resulting the crystal structure is known as diamond cubic crystal structure. So, silicon and germanium are the best example for the semiconductors. Okay, this is the deciding and the most efficient property of a semiconductors. These semiconductors influence the electronic revolution in the hot 1950s. The semiconductors type. This is the diagram which explains the types and the classification of the semiconductors. We all know that the semiconductors are mainly two types. One is intrinsic semiconductor and another one is extrinsic semiconductors. In the foremost diagram, we have explained that this is the diagram, that is the silicon atoms. Silicon, in the silicon atom, you have seen that there are four valence electrons are orbiting around the outermost orbit. Okay, this is the first diagram, the silicons. In the second diagram, you also see that the silicon atoms sharing, how the sharings, the mutual sharing of electron is taken place. In third diagram, it is clearly explains about the how this it is N-type and P-type semiconductors are extremely working. Here in this diagram, there is what is the acceptor, what is the hole. It is acceptor means the electron is accepted. A hole means the electron which is rejected by that covalent bond. We have to see more about the topic. As we see that the intrinsic pure, there is intrinsic semiconductors are pure semiconductor and extrinsic semiconductors are impure semiconductors. The intrinsic, now we have to deal about the intrinsic semiconductor. A semiconductor which does not have any kind of impurities behave as an insulator at 0 Kelvin and they behave as a conductor at higher temperature is known as intrinsic semiconductor or pure semiconductor. Once again I repeat, a semiconductor which does not have any kind of impurities behave as a insulator at 0 Kelvin only and behaves as a conductor at a higher temperature. That is, when the semiconductor is subject to other than 0 Kelvin means that semiconductor will behave as a conductor, extreme conductor. When the temperature of the semiconductor reaches about 0 Kelvin means it will behave as an insulator. This is the important and the peculiar property of an intrinsic semiconductor. As already I told that germanium and silicon are the best example for the semiconductor as well as for the intrinsic semiconductor. They possess a diamond cubic crystalline structure. Here we see about the intrinsic semiconductor is very well explained by the following diagram. We have seen that in silicon, that is the outermost orbit. That is the outermost orbit. There is only one, two, three, four, four. Here it is contributing every mutual sharing of two electrons, which will forms the covalent bond. Here, that is one, two, three, four. Four silicon atoms are combined with the one central silicon atom. So, the mutual sharing of these two electrons combined to form four covalent bonds. That is, two mutual sharing of electrons is equal to one covalent bond. In this diagram, we have the four covalent bond is formed. Here, the outermost orbit is said to be a valence shell. How the bonding is taken place in the intrinsic semiconductor is very well understood by this diagram. Here in this below diagram, it is very well understood how the bonds in silicon. Here it is indicated that germanium, how the electrons are transferred from one germanium atom to another germanium atom. So the mutual sharing of electrons taken place to form a electron. Here in this loss and gain will be losses and gain can be transferred. If the loss is taken place means there will be formation of hole. If the gain is taken place means there is a formation of this electron. This is very well understand. That is sharing, which will in turn produces the loss and gaining of electrons, and it leads to the semiconductors, and the bonds are formed by the sharing of valence electron. Such bonds are called covalent bond. In this diagram, it is how the band gaps are produced in the semiconductors. Here for first diagrams, the energy level for one atom and the energy level for two atom, and for energy level there for three atoms, and for many atoms how the energy bands are arranged. For a one atom there is one forbidden is allowed, forbidden band is allowed, and forbidden energy is allowed. Here energy bands in materials, how the in insulator and semiconductor and conductor is max. For insulator, the band gap is very almost very the band gap is very higher. For the semiconductor, the valence band there is kind of band gap is very small. Eg, the value of Eg is very small, and for the conductor, the band gap between the conduction band and valence band is also very small. So more or less, the semiconductor and conductor having the energy band gap is almost it is approximately something what equal. Okay. But for the insulator the band gap is very high. Comparing to the conductor, the band gap of the semiconductor is very less. For silicon the band gap energy is found to be that is 1.1 electron volt, and for the germanium it is found to be the band gap energy is found to be 0.72 electron volt. The below diagram which explains how the photons and phonons are insisting photons, how the photon is incident to the phonon so that the photon is transferred to another level, another energy gap between the valence band and the conduction band. How the electrons or photons will be transferred from one energy state to another state. So here there are different types of transition takes place. That is direct transition as well as indirect transition. That is direct transition means the photon is directly without any help of energy. It will be transferred from valence band to conduction band. In the indirect transition, there is external energy is required so that the phonon is transferred from the valence band to the conduction band. This is the explanation for the diagram. Here the clear explanation about the conduction band and for the valence band, how the electrons are transferred from the valence band to the conduction band. Here, in this the valence band, there is no all almost it filled with holes. In conduction band, it is almost filled with the electrons. So the kinetic energy of the hole is equal to EV minus E. The kinetic energy of electron is equal to E is equal to E minus E naught. This is the band gap energy for that diagram. Here, indirect band gap semiconductors transfer. How the electron transfer for the indirect band gap and the indirect band gap. For direct band gap, the energy band gap is very higher, and the indirect band gap, the energy band gap is very low. The conduction band can be that is varied in indirect band gap, and for direct band, the conduction band does not vary. So the momentum will be related, that is transited in the constant way. This is the explanation for this diagram, how the direct and indirect band gap semiconductors behave. We know the energy spectrum of the electron moving in the presence of periodical potential field is divided into two zones. One is allowed zone and then the forbidden zone. In crystals, the interatomic distance and the interpotential energy distribution vary with the direction of the crystal. So in the crystal, the interatomic distance depends only on the potential energy. So the distribution will be dependent with the atomic distance and the international potential energy. So it is very well understood with the indirect band gap and indirect band semiconductor. Hence the EK relationship and the energy band formation depends on the orientation of the electron wave vector to the crystallographic axis. In the few crystals like there is gallium arsenide, the maximum of the valence band occurs at the same value of K as far as the crystallographic axis depends. This is the diagram which explains clearly the interatomic distance and also the conduction band and the valence band. Here, the first diagram determines that is insulator. Insulator, that is means the energy band gap between the conduction band and the valence band is very high, means it is said to be insulator. When the energy band gap is very low between the conduction band and valence band, it is termed as there is metals or that is semiconductors. This is very well understood in the previous previous session also. In few semiconductors like silicon, the maximum of the valence band does not always occurs at the same K value as the minimum of the conduction band as shown in the figure. This we call as indirect band gap semiconductor. That is, once again, I recall, in few semiconductors like silicon, the maximum of the valence band does not always occur at the same K value as the minimum of the conduction band as shown in the figure. This we call as indirect band semiconductor. But in indirect band gap semiconductor, the direction of the motion of an electron during transition across the energy gap remains unchanged. Hence, the efficiency of the transition of charge carriers across the band gap is more in direct band gap than in indirect band gap. Here we have to next go to the next topic, that is carrier concentration in intrinsic semiconductor. Carrier concentration in intrinsic semiconductor means we have to depend there is a number of electrons and a number of holes per unit volume in the conduction band as well as in the valence band, which will gives the carrier concentration. We can already know about intrinsic, nothing but a pure semiconductor. When a suitable form of energy is supplied to a semiconductor, then electrons can transition from valence band to the conduction band. Hence, a free electron in the conduction band and simultaneously free hole in the valence band is formed. This phenomenon is known as electron-hole pair generation. This can be taken place only in the intrinsic semiconductor. In intrinsic semiconductor, number of conduction electrons will be equal to the number of vacancies or holes in the valence band. We can know how to calculate the density of electron. Density means mass quantity of content in the matter in a body per unit volume. How many electrons present in unit volume. Then we can take in place the d and be the number of electrons available between the energy interval E and E plus dE in the conduction band. dN is equal to Z of E dE F of E. Then N is equal to lower mode is conduction band energy to the top of the band. That is Z of E, integration of Z of E F of E dE. Consider C equation number 1. Here Z of E is the density of states in the energy interval E and E plus dE, and F of E is the probability of electron occupancy. Then we have already know that the density is nothing but number of energy states per unit volume within energy interval E and E plus dE. Z of E dE is equal to 4 by h cube 2m or 3 by 2 e power 1 by 2 dE. Z of E dE 4 by h cube 2m That is star means effective mass 3 by 2 e power 1 by 2 dE. E starts at the bottom of the conduction band EC. Z of ED is equal to 4 by h cube 2m E 3 by 2 E minus EC power 1 by 2 dE. Probability of an electron occupying an energy state E is given by f of E is equal to 1 by 1 plus e power E minus EF by kT. For all possible temperature, E minus EF is very greater than kT. Therefore, f of E is equal to 1 by e power E minus EF by kT. F of E is equal to e power minus E minus EF by kT is equal to e exponentiation, that is e power EF minus E by kT. Substitute z of e after finding the value of z of e f of e values as equal to in the equation 1. Therefore, n is equal to z of e f of e d is equal to n is equal to ECF. This integral of there is infinity to 4 by h cube 2 m e to the power 3 by 2 e minus EC power 1 by 2 e power E f minus E by kT dE. N is equal to 4 by h cube by 2 m e 3 by 2 integral of lower that is EC to infinity E minus EC power 1 by 2 exponentiation E f minus E by kT dE. Therefore, n is equal to 4 by h cube 2m power 3 by 2. Exponential time is taken out. E power E f by kt. Integral of EC to infinity E minus EC by power 1 by 2 e power minus E by kt dE equation 2. To solve equation 2, let us put the partial integration, that is substitution integral method. E minus EC is equal to x, E is equal to EC plus x, dE is equal to dx, n is equal to 4 by h cube 2m e power 3 by 2 e power ef by kt integral of 0 to infinity E minus EC power 1 by 2 e power E minus by kt dE. N is equal to 4 by h cube 2m e power 3 by 2 e power ef by kt 0 to integral of x power by 2 e power minus EC plus x by kt dx. N is equal to 4 by h cube 2m e power 3 by 2 e power ef minus EC by kt integral of 0 to x power 1 by 2 e power minus x by kt dx. Equation number 3. We know that 0 to infinity x power 1 by 2 e power minus x by kt d is equal to kt power 3 by 2 pi power 1 by 2 by 2. Substituting equation 3. Therefore, n is equal to 4 by h cube 2m e power 3 by 2 e power E minus ef minus kc by kt power 3 by 2 pi power 1 by 2 by 2. N is equal to 2 into 2 by m e kt power h by h square power 3 by 2 e power ef minus ec by kt. The above equation represent the number of electrons per unit volume of matter in the intrinsic semiconductor. We already know that number of electrons in the conduction band is equal to number of holes in the valence band. Then we have to see about the number of holes. How much density of holes in the valence band is nothing but Z of E dE is equal to 4 by h cube 2m power 3 by 2 e power 1 by 2 dE. Since EV is the energy at the top of the valence band, therefore Z of E dE 4 by h cube 2m h 3 by 2 power 3 by 2 EV minus e power 1 by 2 dE. Then EV is the energy of the top band, therefore Z of E dE is equal to 4 by h cube 2m power 3 by 2 EV minus E 1 by 2 dE. Substitute that is Z of E and 1 minus f of E values in equation 1. Therefore, P is equal to bottom of the band EV Z of E 1 minus f of E dE. Therefore, P is equal to minus infinity to EV 4 by h cube 2 m h power 3 by 2 EV minus E by power 1 by 2 e power E minus EF by kt dE. P is equal to 4 by h cube 2 m power 3 by 2 exponential E minus EF by kt integral of minus infinity to EV minus E power 1 by 2 e power E by kt dE. Equation number 2. Then same that we have to solve the substitution integral method. EV minus E is equal to x, therefore E is equal to EV minus x. So differentiating on both sides, d is equal to minus dx, therefore P is equal to 4 by h cube 2m power 3 by 2 e power minus ef by kt integral of minus infinity to EV minus e power 1 by 2 e power k e by kt dE. P is equal to 4 by h cube 2m power 3 by 2 e power minus ef by kt integral of infinity to 0 x power 1 by 2 exponential EV minus x by kt minus dx. P is equal to 4 by h cube 2m power 3 by 2 e power EV minus ef by kt integral of 0 to infinity x power 1 by 2 e power minus x by kt dx. Therefore, finally we get P is equal to 4 by h cube 2m power 3 by 2 e power EV minus ef by kt power 3 by 2 pi power 1 by 2 2. Therefore, P is equal to 2 into 2 by m h kt by h cos h square 3 by 2 e power EV minus ef by kt. The above equation represents the number of holes per unit volume of the material. Then intrinsic carrier concentration. Therefore, number of holes is equal to number of electrons is equal to number of holes. N is equal to P is equal to Ni is called intrinsic semiconductor. Ni square is equal to N into P. Ni is equal to root of N in P. Ni is equal to we get 2 into 2 pi kt power 3 by h square power 3 by 2 me mh power 3 by 4 e power ev minus ec by 2 kt. Here the terms are following term cancel. Therefore, we get the intrinsic carrier concentration is finally Ni is equal to 2 into 2 by kT power h by h square 3 by 2 me mh power 3 by 2 e power e power minus eg by k2 kt. Fermi level. How will you find the Fermi level? In intrinsic semiconductor, we can know that n is equal to p. Now we have to solve how the Fermi level in intrinsic semiconductor behaves. Therefore, we have to put the number of electrons and number of holes. Therefore, here the 2 to cancel and the remaining terms will be put. Therefore, we get exponentiation of 2 ef by kt mh is equal to mh by me 3 by t e exponential ev minus sorry ev plus ec by kt. Taking log on both sides, we get taking log on both sides, that is 2 e f by kt 3 by 2 log of mh by me plus ev plus ec by kt. Therefore, finally, me mass effective mass is equal to effective hole. Therefore, ef is equal to eb plus ec by 2. Thus, the Fermi level ef is located in between the middle of the forbidden band from the intrinsic semiconductor is understood. This is the and the mh is equal to me means that is Fermi energy is located halfway between the conduction band and the valence band. This is the diagram which clearly explains. Next, you have to see about the intrinsic semiconductor, sorry, extrinsic semiconductor. Extrinsic semiconductor, how they behaves. In this diagram, it is clearly mentioned that the external energy is given to so the electrons which is present in the outermost orbit will be um, break and it moves to the forming the free conduction electrons. Okay, so the generation of more generation of these electrons will be occurred. It is accepting and is donating. Because of that, they will be divided into two categories. One is n-type semiconductor, another one is p-type semiconductor. N-type means here it is donates electrons, so that there will be more number of free electrons will be accepted. In the accepting means there will be creation of holes will be created. This is also creation of both there is free electrons as well as the free holes, which will turn and produces there is two different types. One is n-type semiconductor, another one is p-type semiconductor. The extrinsic semiconductors are those in which the impurities of large quantities are present. Usually the impurities can be either third group elements or fifth group elements. Based on the impurities present in the extrinsic semiconductors, they are classified into two categories. One is n-type semiconductor, another one is p-type semiconductor. Here, this is the diagram which explains the n-type and p-type semiconductor. In n-type semiconductor, there will be creation of more number of free electrons. In that is n-type silicon is used. In p-type this boron is used. Therefore, here there will be accepting on electrons. No creation of the covalent bond. There is one sort of electron is needed for creating making the covalent bond. Now we have to see about the n-type semiconductors. When any pentavalent elements such as phosphorus, arsenic, or antimony is added to intrinsic semiconductor, 4 electrons are involved in covalent bonding with 4 neighboring pure semiconductor atoms. The fifth electron is weakly bound to the parent atom, and even for the lesser thermal energy, it is realized, leaving the parent atom positively ionized. This is the diagram which explains the n-type semiconductor. Here, the silicon phosphorus is surrounded by the 4 silicon atom. Here, the phosphorus is considered as a impure atom, it is a donor atom. Here, the phosphorus donates 1 free electrons. Here, there is the free creation of free electrons. This is for n-type semiconductor. The intrinsic semiconductors doped with pentavalent impurities are called n-type semiconductor. The energy level of the fifth electron is called the donor level. The donor level is close to the bottom of the conduction band. Most of the donor level electrons are excited into the conduction band at the room temperature and become the majority carriers. Hence, in n-type semiconductors are collectively said to be a n-type semiconductor. Here in this is the band gap energy for the n-type semiconductor. Here the donor energy level is located nearer to the conduction band, and it is very high, very large away, very far away from the valence band. This is the band gap energy diagram which clearly explains the n-type semiconductor. Carrier concentration. Consider Nd is the donor concentration, the number of donor atoms per unit donor in the material, and the yield is the donor energy level. At very low temperature, all donor atoms are filled with electrons. With the increase of temperature, more and more donor atoms are get ionized, and the density of electrons in the conduction band increases. The density of electrons in the conduction band is given by, already know that N is equal to 2 into 2 by MEKT by h square 3 by 2 exponential EF minus EC by KT. Density of ionized donor is given by NdE power ED minus EF by KT. At very low temperature, the number of electrons in the conduction band must be equal to the number of ionized donors. Therefore, 2 2 by MEKT by h square power 3 by 2 E power EF minus EC by KT NdE exponential ED minus EF by KT. Now, by taking the logarithm and rearranging, we get EF is equal to ED plus EC by 2 plus KT by 2 log of ND by 2 into 2 by ME KT by h square 3 by 2. At 0 Kelvin, EF is equal to ED plus EC by 2. At 0 Kelvin, the Fermi level is Fermi level is lies exactly at the middle of the donor and the bottom of the conduction band. Density of the electrons in the conduction band. We know that N is equal to 2 into 2 by ME KT by h square E power 3 by 2 E power EF by minus EC by KT. And now substituting this, we get E power EF minus EC. EF minus EC, that is for EF, we have to substitute the value. And finally, we get EF exponentiation of EF minus EC by KT is equal to ND power 1 by 2, 2 into 2 by ME KT by h square power 3 by 2, 1 by 2 E power ED minus EC by KT. This by using logarithmic calculation and rearranging, we get the final value, that is n is equal to 2 into 2 by me kt by h square power 3 by 2 nd power 1 by 2 2 into 2 by me kt by h square 3 by 2 1 by 2 e power ed minus ec by 2 kt. Finally, we get n is equal to 2 nd power 1 by 2 2 by me kt by h square power 3 by 2 e power ed minus ec by 2 kt. The final value, that is the density of electrons in the conduction band, is proportional to the square root of the donor concentration at moderately low temperature. This is the value we can find in the n-type semiconductor. How the now we have to see about the how the Fermi level is varies with the temperature. To start with the increase of the temperature, EF increase slightly. As the temperature increase, more and more donor atoms are ionized. Further increased temperature results in the generation of electron hole pairs due to the breaking of covalent bonds, and the materials tends to behave in the intrinsic material. Also, the Fermi level is generally moved towards. Next, you have to see about the p-type semiconductor. The trivalent materials elements such as aluminum, gallium, and indium have 3 electrons ordered to the intrinsic semiconductor. All the 3 electrons of these are involved in the covalent bonding with 3 neighboring silicon atoms. These like compound accepts one external electron. The energy level of this impurity atom is called acceptor level, and this acceptor level lies just above the valence band. This type of trivalent impurities are called acceptor impurities, and the semiconductors doped with the acceptor impurities are called p-type semiconductors. This is the diagram which clearly explains the p-type semiconductor. Here the indium is ordered to the pure intrinsic semiconductor. Here the indium is having the most only 3 electrons, and the one is a sort of forming the covalent bond. So it is acceptor considered as a whole. This impure atom is said to be a acceptor level. This is the diagram which clearly explains the p-type semiconductor. And the acceptor level is located nearly to the valence band, that is EA. And the acceptor level is far away from the conduction band. This is the energy band diagram of the p-type semiconductor. Even at relatively low temperature, these acceptor atoms get ionized, taking electrons from the valence band and thus giving rise to holes in the valence band for conduction. Due to the ionization of the acceptor atoms, only holes and no electrons are created. These holes are more in number than electrons, and hence holes are majority carriers and electrons are minority carriers. The p-type semiconductor. As the same way in the n-type semiconductor, holes are minority and electrons are majority carrier. Next, you have to see about the Hall effect. This is the diagram which clearly explains the Hall effect. Hall effect is nothing but when a magnetic field is applied perpendicular to a current carrying conductor of semiconductor, voltage is developed across the specimen in the direction perpendicular to both the current magnetic field. This phenomenon is called Hall effect, and the voltage developed is so-called Hall voltage. Let us consider the thin. This is the diagram which goes. This is the thin diagram. Here we see that current is applied in the x direction, and the magnetic field is applied in z direction, and the Hall voltage is developed in the y direction. This is the clear explanation for the Hall effect. X direction current direction, if we place magnetic field B which is in y direction, the potential difference is developed between the x and y direction, the p and v correspond to the z direction. This is the for n-type semiconductor, the whole of it is clearly explained. Current in x direction, y in magnetic field direction, z in the Hall voltage direction. Magnetic deflecting force F is equal to QVD into B. Hall electric deflecting force F is equal to QEH. On equilibrium is this, the magnetic deflecting force on the charge carriers are balanced by the electric forces due to the electric field. Therefore, QVD into B is equal to QEH, EH equal to VD into B, where VD is drift velocity. The relation between the current density and the drift velocity is equal to Vd is equal to J by Ne, where N is the number of charge carriers per unit volume. Eh is equal to Vd into B, Eh equal to J by Ne into B, Eh equal to 1 by Ne J into B, Eh equal to RH J into B. RH Hall coefficient is equal to 1 by Ne, therefore that is Eh by J into B. EH equal to EH by D, where D is the width of this slab, RH equal to EH by JB, RH equal to 1 by JB into EH by D, EH equal to RH JBD, A is the area of the cross section, that is cross section area current density, J is equal to I by A, PH equal to RH I by A BD, L is the thickness of the sample, therefore RH equal to VH L by IB. Since all the three quantities E, H, R, J, and P are measurable, the Hall coefficient RH is the deciding authority. If it is positive, means the Hall of RH is positive, means that is the type of semiconductor is uh, n-type semiconductor, and the RH equal to negative means that is that is the RH is negative means the type of semiconductor is n-type, RH is positive means it is a p-type semiconductor. Generally, for n-type, the Hall field is our negative direction about the field level. For a p-type, negative sign is used while denoting the Hall coefficient. Next, you have to see about the applications of semiconductors. Most probably, the major application is LED. LED are promising light source whose efficiency was 10 times greater than the incandescent lighting. Long operating life and reliability has made LEDs as potential choice for next generation lighting system, including automatic, energies, emergency backlight, indoor and outdoor. LED lighting can also be referred to as solid state lighting because an LED is solid state technology. It is the first developed in 1960 and its characteristics decides the light source is suitable for indication and illumination. Indication refers use of the light source viewed directly, self-luminous object, example signs, signals, indicators, lights, and electronic equipments. Illumination refers the use of light source view other object by the light reflected from those objects. Lighting found in the rooms and task lighting in desk. This is the diagram which explains the LED illuminator and LED indicator. What is an LED? LEDs are semiconductor diodes, electronic device that permit current to flow in only one direction. The diode is formed by bringing two slightly different materials together to form a PN junction. In PN junction, P side contains excessive positive charge, holes indicating the absence of electrons, while N side contains excess negative charge. This is the diagram which clearly explains. It is a forward biased one. How LED works. Here, when the negative end of the circuit is hooked up to the n-type layer and the positive end is hooked up to the positive n-p-type layer, electrons and holes start moving and the depletion zone appears in the PN junction. Same way, when the positive end of the circuit is hooked up to the n-type layer and the negative end is hooked up to the p-type layer, free electrons collect on one end of the diode and the holes collect on the other. Depletion zones bigger. This is the principle of the LED. When current flows across the diode, negative electrons move away one and the positive holes move other way. This is the typical LED characteristics. The LED means semiconductor material, gallium arsenide phosphate, gallium arsenide phosphate, gallium arsenide phosphate, aluminum gallium arsenide, silicon carbide, gallium indium nitride. This is the typical LED. Here, for example, gallium arsenide, the wavelength ranges between 850 to 940 nanometer. The color is infrared, and it is find the voltage is 1.2 volt. The higher is the red, that is the gallium arsenide phosphate. The wavelength is 630 to 660 nanometer red, 1.8 volt. The higher voltage for the typical is gallium indium nitride, 450 nanometer, and the color is white, and the voltage drops access to 4 volt. What now makes the LED suitable for illumination application? That is, LED construction has also changed to make them more efficient. The crystal forming early LED junctions are very grown on light absorbing substrate material. Using the substrate, transparent substrate, and optimizing the step of the semiconductor element have increased the amount of light able to give the device. Most common application of semiconductors are that is displaying lighting. Compact displays are possible with low operating temperature. Display case, museum and shop lighting, illumination of sensitive object at close range with ultraviolet and infrared free light, underwater lighting, low voltage supply for free safety and low maintenance. Outside lighting, colored effects to enhance the outdoor spaces. Sign lighting, strips of LEDs can be used to light signage in many different colors. Low level lighting, LED luminaries are cool to touch and are therefore suitable for us in domestic situations where children may come in contact with them. Architectural detail lighting, LEDs can be used in application which traditionally used for neon and cold cathode. Thank you.